All right, so now we're starting in the next section of our book under single loop circuits, and this makes a nice unit actually. I don't think we need to test immediately after doing single loop circuits, because we can also then do multi-loop circuits and just put it all in one test actually. Okay, so kind of like we did with resistors and capacitors, we put it all under one test. The same thing with single loop and multi-loop circuits. Okay, so the first thing we need to understand is that there's two kinds of batteries in theory, and there are only one kind of battery in real life. Okay, so batteries can be real or ideal, as in like perfect. And also you need to understand that batteries are not the only suppliers of energy also. So that's another thing. We're not going to discuss some of these other things, but there are other, sources of work, right? There are other sources. Batteries are just one of those sources. So I'm going to pause the video and see if you remember some of the other ones I mentioned the other day. So another source of energy to make sure work gets done is a generator, which is not the same at all as a battery. Batteries use what kind of energy to supply work, or to supply more energy for work? What kind of energy is being used there? Good, a student answered uses chemical energy. Generator, though, uses something else. So the generator actually doesn't use chemical energy per se, it uses mechanical energy, right? There are others besides battery and generator. Another one is called a thermopile. And a thermopile gathers energy from heat. It's basically converts heat into energy. So, you might put thermopiles near like a nuclear power plant or something. There's so much heat generated in certain regions of our world. You might put thermopiles nearby because they can basically turn that into a useful form of voltage and therefore work. Okay, so thermopiles get their energy from convection and conduction and radiation of heat. So it absorbs heat and dispenses it as voltage. Okay, and one that's becoming increasingly popular in the field of scientific technology. So, yes, solar panels, somebody said. Or perhaps you've heard of photovoltaic cells, gathering energy from light and turning it into useful forms of voltage. Okay, anytime one of these is doing its job properly, we get voltage. Anytime we get voltage, we can move charges. They are all, in a sense, charge pumps. So these are all charge pumps, as our book likes to say. And I like the word pump actually because a pump moves water, and we call the flow of water, what do we call the flow of water? We call the flow of water current. And a charge pump moves charges, and what do we call the movement of charges in coulombs per second? Yeah. So current. And that just makes it a nice analogy and a great choice of words. Okay, so current sounds like almost like water then. Okay, dissecting the battery comment. I already did this the other day, but a battery can be either real or ideal. Let's look at ideal first. The ideal battery has an internal resistance of 0. But a real battery has an internal resistance that is non-zero. So it has a small resistance of its own. And the nice thing about an ideal battery is that 14 volts, when not in a circuit, still means 14 volts when in a circuit. So, you know, has same voltage, supplies, I should say, it supplies the same voltage in or out of a circuit. Or some people like to say under load and not under load. On the other hand, the real battery, which is of course what we have to live with, they have a slight voltage drop as soon as they're connected into the circuit. So has less voltage when in the circuit. Okay? All right. Now, because we're pumping, right, it just feels like a push. And so we'll stop using the word voltage when talking about a battery, and we'll adopt a new word, electromotive force. The units are still volts, okay? But it's just a word used with any charge pump, and the symbol is, of course, E. Kind of make it look pretty, if you can. Electromotive force. And you will see this symbol all over electrical engineering books. All right? If you must know its definition, it's dW dQ. And instead of thinking of this as, like the derivative of work with respect to charge, if you want to, you could just think of it as the amount of work to move, or excuse me, it's the amount, think of it as the work per unit charge that it can supply. So how much work can it give to a little dQ? That's the EMF. If you think about it, this is not very different from what we wrote a couple weeks ago when we wrote the potential energy stored in a capacitor is U over Q. It's exactly the same equation, actually. But it's pumping little dQs using a little bit of dW, which happens to match du. So a lot of times our potential energy and our work are equal. You know what I mean? So sometimes we use W when we mean to write U and vice versa. It's because we're dealing with conservative systems on the most part. Okay, so what I'm saying is, I'm not saying these are the same equation. I'm saying you can kind of agree that this does look a lot like what we wrote just a few weeks ago. Okay. All right, so I don't care if you call it voltage too much, but you're going to see E all over the place. All right? All right, so instead of saying a constant voltage supply, we might want to say a constant EMF supply or EMF device. All right, now it's time to finally talk about circuits. So let's say you start with a circuit, and I'm going to start with the one that they do in the book. They start with a battery and a single resistor. Seems like a good place to start. And I think I mentioned this earlier, but for some reason scientists decided to go ahead and allow this current to follow the path from positive to negative. So it's kind of an unfortunate convention, partly because we know that it's actually the electrons that are making the real journey. So we don't say the positive charges are moving, we just say the positive carriers are moving, which means the carrier pattern is moving. So as the electrons race this way, they leave behind them a group of positive ions, I guess you could say, and it appears like positive going clockwise. Okay? Another way to think of it is, if you're sitting in a car, right, and you're sitting up next to a big bus, you've probably done this before. You're sitting next to a bus, you're in a car, right? So you're the little blue car, and you're sitting next to a bus, and then the light turns green, and the bus starts moving forwards this way, let's say. You get this funny feeling that you're moving backwards, even if your father hasn't stepped on the gas yet, right? It's kind of like that. So It's a relative thing anyway, and scientists chose to go clockwise, or not clockwise, but positive to negative. All right. Now, the current all of it passes through the resistor, all of it. None is lost, and the reason is, well, there's no branching of the circuit. So you know how water gets lost, right? Like you lose water if there's what happens if you have a pipe and you're pumping water through it, right? Why would there ever be less water coming out than going in? Like if you noticed, hey, I put in 2 gallons, but I'm only getting 1 gallon out, you should probably think about why that is. So the only reason we could lose current is if it had another place to go. So whether it's a leak in the wall, or perhaps there was another pipe that you weren't aware of, and the water had 2 choices when it got to this fork, right? But in this particular situation, all the current goes through this resistor. How do we know? There is no other path. Okay? All right. So the current in the circuit is I, and the current through the resistor is I. That's all I'm trying to say. All right, now we know that I is dq dt. I think I made that clear earlier in the lessons. I said that I is the rate of change of charge with respect to time. I know I told you it was coulombs per second, but this is sort of the definition of I. All right, so if you're going to do work on a charge, right, then you need to supply a voltage. And the voltage being supplied is the EMF. And we're applying it to the charged element dq. And so if you wanted to, you could think of the dq as I dt. So it would look like this. I got that from the equation above it. So I just changed the dq to I dt. All right. So how much work is done by the battery to move a dq? E I dt. Okay. Well, by the time it hits the resistor, what's the resistor going to do with that work? It's going to dissipate it into heat, warmth. Okay. So conservation of energy, this is all just straight out of the book. Conservation of energy dictates that the resistor, which is the only other element in the whole circuit, would dissipate this energy. So while the battery is supplying the energy, the resistor is dissipating it all. And the amount it dissipates is according to P equals I squared R. But this is dW dt equals I squared R. Okay, so from the resistor work, we see that dW is I squared R dt, but the battery is supplying electromotive I dt, so we could set these equal, and then I'll take your question in a second. So we have electromotive force I dt should equal I squared R dt. One of the factors of I cancels out. The dt cancels out, and we get Ohm's law. Okay, now in a single resistor circuit, Ohm's law is V equals IR. Done. Right? In other words, the only equation really for this circuit is E equals IR. And that was taught from an energy standpoint. Okay, so what I just came up with is just a rederivation of Ohm's law. And it's under the assumption that the EMF provided by the battery is equal to the current in the circuit times the resistance of that resistor. Now this is all an ideal battery actually, because I never actually considered the option that there's two resistors in this circuit. So now I want to remind you that technically there are two resistors in the circuit, one big R and one little r. So if you kind of go back to here and you imagine that there's a little resistor inside the battery with resistance little r, I don't want to rederive everything, but technically now you could just treat the total remember these are in series, so this little r and this big R are in series. So how do we add them? So you answered correctly, we just add them as is, R plus R. So you could replace this with R plus little r if you wanted to talk about the real situation as opposed to the ideal. Okay. Now, there's another way of thinking about this, and it was a guy named Kirchhoff who came up with this next comment. And it's a really profound statement, very profound. And he said, basically he said this: the sum of the changes in potential differences in one loop, any loop, is always zero. Is always zero, okay? So here's what he's saying, and it actually makes a lot of sense, especially after what we just talked about. So let's draw the circuit again one more time. Okay. Let's go back to the ideal case where we don't really worry about the little r. So there's just one big R. What is the voltage supplied by this component of the circuit? If you just circle this part of the circuit, we call this contribution to potential difference electromotive force, right? Okay. And then this contributes some voltage also. You might say, what do you mean? It's not a voltage source. I agree, it's not a voltage source. It's actually a voltage drain. Okay? So all of this E must be lost over here. All of it. So the voltage sum has to be zero if you look at the components. We know the battery supplies the EMF. So what exactly is the R wasting the EMF? So think of this as your X. And look at Kirchhoff's rule. He said if you add E and X together, you're supposed to get zero. Well, what does that tell you? That tells you that X is negative E. You see? And since E, remember, was IR in the ideal case, X is negative IR. So what are we saying? We are saying that, well, first of all, Kirchhoff had a cool little trick here. Okay. We are saying that the voltage in the resistor, or supplied by the resistor, is a negative voltage. What the heck does that mean? It just means that the resistor causes a drop in voltage. So it's like a voltage dropper. Voltage dropper. Okay, so the voltage supplied by a resistor, you can think of it as negative IR. This is in a single loop resistance and battery situation. Okay, now you might be bothered by this, but I want to remind you, if I just had a loop of wire and there was no battery and there was no resistor, what would be the potential difference between points A and B? No battery, no resistor, just a loop of wire. What do you think? What would be the resistance, or what would be the the voltage difference between these 2 points. Okay, now I squeeze in a battery. A battery only. What's the voltage between these 2 points? Hold on. Okay, so the EMF is the only charge pump in the problem. And the wire itself would then act, the wire itself would then act as a resistor and provide a negative EMF over here. So the wire itself would dissipate all of that. And the sum would be 0 going around. It's always 0 sum going around. In other words, with the E or without the E, it's an equipotential surface on the right. So we can't have any change in voltage between the 2 points. So hopefully I'm explaining it clearly. It's very similar to, let me say it this way. Let's say you have a water pipe in your house, and it goes basically down and through the attic, down into the basement, like this, right? That was a really bad drawing. I was going to draw a pipe that goes like this, down into the basement. I don't know why it was so hard to draw the first time. Okay, so the height right here is analogous to the voltage. So like a waterfall, you know, there is potential to be converted here. Okay, so the water will make its way down the pipe and flow out the bottom, right? You won't lose any water because there's only one path for the water. So the current will remain constant and the voltage will remain constant, right? But if you have a loop, that means the water pipe returns to where it was in the beginning somehow, right? You don't have any height. There is no height here. The pipe returns back to itself. So what is the ability to do work? 0. There is no ability to do work. Any positive heights that were in here are now all canceled out by negative heights, if that makes sense. In other words, there is no ability to do work. Will there still be motion? Maybe, but it's going to have to come from some outside source. Maybe a fan blowing the water like through a small opening here, and then it just shoots around because it's being forced to. Or maybe it's electrically charged fluid, and it's going to move because there's magnets in the area or something. Okay, so kind of confusing, but actually it's very simple to use this idea when working in a circuit. So let's say you have a battery here, and that supplies 3 volts, and then this is the positive end, this is the negative end, and then you bring it over here, and this is connected to another battery, and that supplies 2 volts, and then over here you have a resistor. Okay, so as you go around, you'll notice something, the reversed polarity on these. Okay, so now watch this. The EMF, if you remember from the other day, I don't think I mentioned this today yet, but I had mentioned EMF last week, and I said that EMF should always be drawn from the negative side of the battery to the positive side of the battery. So this is going to provide an EMF for this battery, and this is going to supply an EMF too from this other battery. So we have 2 EMFs on this problem. Okay, and we draw a little circle there on the end. That's just how we draw the EMF arrow. But it always points from the negative terminal of the battery to the positive terminal of the battery. Okay, so you might realize that this is really just a 1-volt battery, actually, because you have basically one of the EMFs is pointing at the other. So honestly, if you take a 3-volt battery and a 2-volt battery and you try this experiment, you're going to get 1 volt to do work with, right? Okay, so what's going to happen is you're going to start with calling this a +3 right here. And then when you get over, as you go around the loop, you just kind of pick a direction and go around. It doesn't matter which direction. As you go around, you're going to take the algebraic sum of all the sources you find. Okay, so we'll just call this one X for now. Okay, so we'll use red. This one's X, whatever. Okay, so you go around the outside. So you say, all right, let's see, I start with a positive 3, and then I hit this negative 2. So this is an algebraic sum, right? Not just a sum. If there's a negative, put in the negative. What did we say about resistors? We said that a resistor, would that be a voltage source, or is it more of a voltage drain? That's correct. Students answered that it's a voltage drain. Should we use a positive X or a negative X here? So recall that X is I times the total. It's IR. Negative or positive is the question. Do we use negative or positive? Is it going to contribute more positive voltage, or is it going to tend to drop the voltage? So because it's dropping the voltage, we're going to put in a negative IR here. And then this is what we would call the loop equation. Okay, this was not terribly interesting because it just gives you the statement that IR is 1. But if you knew the resistor's resistance, you could plug that in and figure out how much current there is in this circuit. So Kirchhoff's law is a voltage statement. It makes a statement that the changes in voltages as you go around is always 0. But the outcome, what you learn from it, is the current, actually. So I'll say that by putting in a number. Let's say that the resistance is given to be a 10 ohm resistor, right? Then you could put that in. And this is all equal to 1 what? 1 volt. Remember, it was the sum of voltages. This is 3 volts minus 2 volts is 1 volt. And then when you divide, you get literally I equals 0.1 volts per ohm. What's another way to say volts per ohm? So this is just I equals 0.1 amperes. So Mr. Shore is just basically kind of talking you through the story here. Kirchhoff said the sum of the voltages, whether positive or negative contribution, is always 0. And of course, if it's going to be 0, some have to be positive, some have to be negative, or they're all 0. And then from writing any Kirchhoff loop equation, the payoff is we get current. Or maybe they give us current and we don't know the R. Actually, we could have found resistance knowing current. All right, let's draw another one. Just kind of play around with this concept for a few minutes. Let's say you have a battery here, and it has EMF we don't know. And then this goes around to resistor 1, which is 100 ohms. And then there's another branch. Oh, we'll have to pause. I'll stick to one loop. I'll finish this example real quick. But then let's say you have another battery here. And let's say that this is, our EMF is supposed to have a little circle on the back. Let's say that this EMF is known. It's a 3 volt. So this EMF, we don't know. We'll call E1 and E2 again. Okay, and then I told you that the current in the circuit, let's say, was 0.2 amps. So all you have to do is just don't worry about the 0.2 amps. Just kind of get the ball rolling and run around the circuit. We'll start here. Doesn't really matter where you start. The first thing we do is we pass through the battery and we pick up a positive V. We hit the resistor and we subtract off IR. We then hit the other battery and we pick up a positive 3. And we loop all the way back home plate and we put 0. This gives us 4V. Sorry, we don't need the V here. V is unknown voltage. So this gives us V plus 3 equals IR. And we know I and R. So let's isolate V actually. So it's IR minus 3. They told us I was 0.2 amperes. They told us the resistance was 100. And we end up with V equals 17 volts. So I just basically formed an equation by running around the loop. adding up the changes in voltage as I went. Anytime I hit a battery, I add if the battery's in the same polarity as the other. I subtract if they're reverse polarized. If I hit a resistor, I'm going to do a minus IR every time, and I set it equal to 0. And then I isolate whatever it is I need, which is usually what I'm not told. This can get harder with multiple loops, but it isn't a lot harder. It just gets to where you have lots of these equations, and you have to solve them as a system. Okay, and I also thought of a way that I could actually create another problem that looks like a multi-loop circuit, but actually it isn't. So let's show this one. Okay, let's say that you have a battery like this, and we're learning that you can draw the little EMF symbol this way. This just helps us understand, you know, if we're going to go clockwise around the loop, we're going to count this as a positive EMF. And let's say you come up to here, and then there's a branch in the circuit like this, and let's say these are both, 10 ohms, and let's do 30 ohms, like that. And then this comes around and around and around, and then it comes over here, it hits another battery, like that. And there's another circuit here, and then that's a 20 ohm resistor. Okay, so the second battery would have an EMF pointing this way as well. I say pointing this way as well because E1 and E2, if you're going clockwise around the circuit, right? If you're going clockwise around the circuit, technically both of those are pointing in that direction of travel. So, in a rotational sense, the two red arrows are pointing in the same general direction. Okay, so you can start anywhere you want actually, but the problem is this looks like a multi-loop circuit. So what I want you to do is just go ahead and, find the combined resistance of these two so that they really can be replaced with one effective resistor. So if you remember, these are actually in parallel. So whenever you sum up resistors in parallel, you basically have to sum up the reciprocals, and then you put them all under a 1, and this gives you the resistance total, or effective resistance. And again, we're considering the batteries to be ideal. But you know what? If you suspect that there's a resistance within the batteries, then you can diminish E1 to its real value and diminish E2 into its real value because, well, they're diminished anyway. So actually, usually if we pull them out like this and we just look at them without the circuit and we just look at the battery itself, we would call it a voltage. But once it's in the circuit, it's going to be a slightly diminished voltage, and we call it the EMF. So when these are labeled E1 and E2, they already have kind of subtracted off the internal resistance voltage drop. So these E1 and E2 are perfectly accurate for a circuit. We don't need to include little resistors inside the batteries. Okay, now let's go to the idea that we can combine these into 1. So you'll be adding 1 over 1/10 plus 1 over 1 plus 1 over, I can't write on the edge of my screen, obviously, so let's try that again. The resistance is going to be 1 over and then 1 over 10 plus 1 over 30. So the bottom comes out to be 40/30ths. And the reciprocal of that is 30/40ths. So it's interesting to me that these two combined resistors basically make a pretty worthless resistance when put together like that. It's just 0.75 ohms. All right. Now going around the purple loop, we will follow Kirchhoff's general rule. The sum of all the potential differences, some positive, some negative, should add up to 0. So let me go ahead and hold on a second. Let me grab all this and shrink it a little so I can still see my circuit as I scroll down the page. Okay. Let's put that at the top. All right, so Kirchhoff said, look, let's go around the outside, and I see this now as a single resistor. battery, resistor, battery situation. So it's one less, I guess, resistor. So this is an effective resistance of 0.75. Then down here we still have this 20 ohm resistor. We still have two EMFs, and they're both contributing voltage when you go clockwise. So this one was E1 and E2, and I probably should have given you values for some more things here. So let's just go ahead and solve it and see what we get. And if we need more values later to get numerical answers, we will. So, but basically Kirchhoff said, let's just go around the loop-de-doo, and we will start. We'll start, just to make things different, we're going to start right where this green dot is. Okay, so starting there and going this way around, let's see, the first thing we encounter is this E2. It is got its EMF arrow pointing in the direction of our motions, so we will put positive E2. Then we hit this darn resistor next. Resistors resist us, so we would put negative IR, and the R is clearly 20. And then we hit a battery again, and the battery ups the voltage again, so by an amount E1. And then we hit the top resistor, and it's an effective resistance of 0.75, but it is in a sense an energy drain, right? So we are going to do minus and then I times 0.75. And then this is the end of our journey. We've hit all four components. We then write 0. And from this we learned that E1 plus E2 is, and then you can just group like terms together and move everything to the right side, 20.75 I. Okay, now I could give you two of these three things. I could give you like E1 and I, E2 and I, or I could give you E1 and E2. Most people know what their batteries are, right? So let me just give you the E1 and the E2. Let's pretend that E1 is a 12-volt battery and E2 is a 3-volt battery. So very different voltage pumps, or charge pumps, but let's just put them in there just for fun. So this would be 12 plus 3 equals 20.75. In other words, I is 15 over 20.75. And then let's go ahead and get a decimal for that. It's 0.723 amps. Okay? All right, so you can kind of see how this works. Even though it looks like a two-loop circuit, what we really mean by two-loop circuits is when you have a circuit and in one of the loops there's a battery, and then in the other loop there's a battery. So what we're not quite prepared to do is do this problem where you have a battery and then this connects to a resistor, and then this has another battery. Like, we could probably do this problem, but then there's another loop over here with another battery or another resistor. Okay, so the reason this isn't something we are ready for yet is because if you look at this, there's really two loops. There's the yellow loop, and then there's the green loop here, you see. And each of them has a charge pump in that loop, okay? So this is multi-loop circuits. We'll deal with this when we get to it. It's next chapter. And you basically have to set up Kirchhoff twice. Once you've set up Kirchhoff twice, you then need to also impose a conservation of current equation onto those two Kirchhoff loop equations, and then you end up with yourself getting a pretty messy problem and three equations at least. One for each loop, plus actually a couple more, two more. We have conservation, current conservation equations, plural. So we'll deal with it later, but right now, if there's one loop, or the problem can be topologically converted to one loop, you should be able to handle it. And we know how to combine resistors into a single element, so it shouldn't be too difficult. This is really a one loop problem in disguise.